Hello, everyone. Today I'm going to talk about training a segmentation algorithm and causal ML in the context of working with tabular data. So I just want to wish everybody a happy Pi Day. So hope you're having a great Pi Day. So just to jump back into the basics of deep learning, previously we talked about the anatomy of a neural net where you have an input layer. That is the data that you're bringing in, normalizing, and then passing through the neural net. We have the model weights, which are the parameters that are learned during the training process. They can amplify or dampen the input signal, influencing the network's output. We have optimizers that basically introduce nonlinearity into the model along with the activation function. So the optimizer is focused on minimizing the space that we're trying to learn because neural net is a function approximator. It's a universal function approximator, and we want to find the minimum of the space. So the activation function introduces nonlinearity. We have ReLU, sigmoid, and 10H, which are common activation functions that introduce a way of mapping input to output in a nonlinear fashion. And then we have the loss function. That's a metric that we're actually trying to learn. So we have something like the mean squared error for regression tasks or cross entropy for classification tasks. And then we have the output layer, which is the prediction that we're ultimately receiving after training the model. So we want to minimize the loss between input and output, between predicted and true with a given input. So for imaging applications, the most successful solution that's been created to date is the CNN, so the convolutional neural net. This was developed by Jan LeCun in 1989 while he was at AT&T and Bell Labs, and it was actually developed for zip code recognition. So we have some common pieces that are used to create a CNN. So we have an input, which is basically a patch. We have a convolution layer, which takes a patch and convolves it into a smaller representation. Then we have a pulling layer, which will take the max of that patch and then pull it forward. So it's basically a bunch of convolution and pulling layers that learn features within an image. So it's basically like learning a feature as it goes through a 2D image. Again, we have the same building blocks, the activation layer that we saw before that introduces nonlinearity. And then at the end, we have an output layer that often uses a softmax layer for generating a probability output. So some additional techniques that are used are dropout and batch normalization, which can help with the generalizability of the solution. Beyond that, it's a very common architecture that has been very successful. A lot of solutions are kind of built on this. So I'm going to talk about one of those now, which is the UNet architecture. This was developed at the University of Freiburg, Germany for biomedical image segmentation. So this is kind of the go-to solution for segmenting regions of interest within an image, like within the context of radiology, like trying to segment a tumor or segment out something which would be of interest. Basically, it's an encoder-decoder system where we take data, we encode it, and then we decode it. There's some skip connections in between which allow for sharing features between these layers from the encoder to the decoder side. But basically what we're doing is we're taking an input, an image, and a mask, and we're learning what those masks are for the given image. And we're able to utilize this architecture fairly reliably to determine, to predict a mask for a given image. And this is a very common architecture, which has a lot of key strengths in terms of working with small training sets and finding features which can be used to segment out a region of interest. So I'm going to jump into actually training a UNet now. So this is a demo which I built utilizing Monai. So Monai is a set of libraries for medical imaging that was developed by NVIDIA. So they have some UNets that you can pull off the shelf and immediately use to train a model. So I'm just going to go ahead and run this. And as it's running, I'll explain some portions of the code. So it's a fairly simple PyTorch code where we install the needed packages, we import those packages, and we download an example dataset. So I'm downloading a spleen segmentation dataset that has a bunch of masks and images associated. So this is a 3D set of spleen images. So there's 41 total images, and we're splitting that in a 80-20 split. And we're actually using 32 for training, and we're using 8 of those or 9 of those for validation. So the very first thing that we do is we pull the dataset, and then from there we generate a dictionary which has the images and labels so that we can use those to actually pull in the data. So we have the train test split that we're using to generate a split of training and test data randomly. Right now I have it turned off, but you can use this line to generate a random train test split. Right here, I'm just actually using all except for the last 9 for train and the last 9 for validation. But going forward, I set up a number of transforms to load the images and basically scale and crop appropriately. So these are some transforms which are useful for preparing the images for use in the neural net. Going forward, I create a data set and a data loader. So this is one of the key components after you load in and transform your data, or the transformation actually happens at this level. But you pull in raw images, you create a data set and a data loader, and then you can actually use those to train a model. So the model is a UNet architecture. This is just pulled off the shelf from Monai. So it's very simple to just say that you want to use a UNet. You can specify the number of spatial dimensions, the number of input channels, output channels, the strides that you want to take. So these things are kind of tunable, the strides and the channels. But the rest of these, they're somewhat dependent on the size of the image that you're pulling in, but you can always pad to make it a certain size. But in this case, we're just specifying some parameters before we utilize the model, and we're going to use a GPU to train the model. Going forward, we now have a model definition. We have a data set, and we can actually step into the training loop. So the training loop is your standard training loop where you loop over a number of epochs for the given data set, and we are minimizing the loss, which in this case is utilizing the dice metric. Let me see where I have that specified. Yeah, so I have the loss function as dice loss. So this is basically a metric which looks at the predicted pixels that are true versus false. So it's kind of like looking at the integration over union. It's a similar metric to that, just to see like how many pixels are predicted properly versus improperly when doing segmentation. But we have our standard training loop that it'll work through. And then as it completes, we plot the loss curve, and then we can actually run inference and look at the prediction on a batch of data. So I have some functions here for doing inference and then visualizing the data. So right now the code is running. Let's see like at what step it is. It takes a little while. So it's loading the data set right now. This is like something like 100 gigs, or sorry, no, 1.5 gigs of data. So it's still fairly large. This code takes a little while to run, but we'll let this run in the background, and then we'll come back to this code and look at the results. See. So we have an example for training a UNet now, and this will be shared with everybody. This is built off of a tutorial that was provided by NVIDIA. Again, I'm happy to sit down with people individually and teach them how to train models for their own applications if needed in the future. And then going forward, I want to talk about the MedSAM model again. So the MedSAM model is right now the state of the art for segmentation. It utilizes a multimodal based approach where you can pull in your own data. It's a model which has been fine-tuned for medical image segmentation. So this is a multimodal solution where you can use bounding boxes, or you can use points to segment data within your own or from your own practice. I also have some examples where you can fine-tune it with your own data. So if you have segmentations that you've done manually, you can fine-tune it. But for today, I'm going to step into a MedSAM tutorial where you can look at inference. So basically, this is an example of how you can take MedSAM and you can use it for your own data. So this is developed by, I forget at which university they were at, but this pulls in their GitHub package where they set up everything. Basically, we're setting up some functions for showing the mask, showing the bounding box, and then actually doing the inference. So with this code, you can pull your own data set. So we have some example data that we're pulling here, and we have the MedSAM model that we're pulling. And then we're actually just going to use that model in reference. So we're using a particular checkpoint from their training. But if you wanted to fine tune the model, you could fine tune it and create your own checkpoint and then use that. And I'll share some other code on how to train or how to fine tune MedSAM. But in this example, we're just going to let it run and show how you can use MedSAM for your own inference. But this one runs a little bit faster than the UNet model because we're actually training the UNet model versus this is an inference where we're just taking a model which has already been trained and applying it. But in terms of fine-tuning the model itself, it's not that difficult if you have your own data and you can use a smaller amount of data. So that's one of the advantages of transfer learning is if you already have a model which is fairly good at predicting segmentations or whatever, you can take that model and then you can fine-tune it with a very small amount of data and make it good for your own applications. When you fine-tune, I would recommend still having a diverse distribution of data points to work with though. So like, for example, you'd want to capture with the minimal amount of data, all potential cases that you would see for different disease presentation or whatever you're actually trying to segment. But the main point is you can use a small amount of data. It looks like this might take a little while to run as well. Let's go back and check on the other notebook.
Say a little bit of data. What do you mean? Can you define that? Like in this realm, like they can be wild different.
Yeah.
Little versus large.
Yeah. So a little bit of data would be like on the order of 50 to 100 data points. So if you have 50 to 100 data points, you can take this off-the-shelf MedSAM model and you can fine-tune it for your own applications. So yeah, like I feel like 50 to 100 is achievable. Like in a clinical study. What are your thoughts?
I mean, I feel like not all clinical studies are created equal. Probably depends on what you're looking at.
Yeah, but I mean, I would assume that you would like, regardless of the study, you'd need a statistically significant number of samples. So for whatever you're doing, I would assume that that would be on the order of tens of data points at least, or like between like 3 and like hundreds. So I think also because in segmentation, if you're working with 3D volumes, depending on the number of slices that you have as well, that can impact it. So like if you have many slices but fewer patients, you would still have a lot of training data. So yeah, it depends on the number of patients and the number of slices that you have, but I would say that you would need on the order of hundreds of slices to train a good model. But like in this UNet example, it utilizes 32 training points and 9 validation points. And when this finishes running, it gets to a die score very close to 1, which is pretty good. But like again, you'd need to evaluate that on another validation set to verify that it is working correctly. But with 32 data points and 9 validation points, this gets very close to an IOU or die score of 1. Yeah. But it looks like this is still running. Might take a little while, but let me go back to the other one and see what it looks like. Yeah, so in this example, it ran more quickly, and we're just pulling a single image, and we're providing an input in a bounding box, and it's able to segment this pretty easily. I also have a tutorial, well, not really a tutorial, it's more of an app where you can just drag in images and draw a bounding box like this, and you can use that to do segmentations. But the main point is MedSAM is fast, and it's already trained, so you can use it, and it's been trained with a lot of radiology data. So this is something that is almost plug and play. Like you can plug it into an application and use it, and that's what a lot of people are doing. But it's also fine tunable. Keep losing my presentation. So we've touched on UNet architectures, and we've touched on segment anything model. So the performance of segment anything model compared to UNet is very close. Segment anything model is a little bit more generalizable and easier to use. It's a multimodal solution that supports using bounding boxes, points, or actually even just text. Like you can say segment out the spleen, and it should be able to do that by itself. So this is the latest in terms of segmentation. And then I also wanted to talk a little bit about causal learning in healthcare. So causality is pretty important. You have correlations that you can learn with linear models, and you can say this thing goes up when this other thing goes up, or this thing goes up and that one goes down. But in terms of working with tabular data, being able to understand why something changes is important. So I'm going to talk about causality and how it can be used in the context of tabular data or clinical studies with tabular data. So we can learn effective treatments from patient data, distinguishing successful interventions from coincidental recoveries. We can use this in a large number of domains, from like drug discovery to like looking at how certain factors impact treatments. So causality is super important for evidence-based insights. Understanding the causal pathways of A causes B causes C is super important as well.
Like causality is so hard to like actually prove.
Yeah,
that it's interesting that it's the whole concept of causation, because usually it's correlation with those outliers. I'm like, I don't know, it's just
yeah, this is something that is starting to gain more traction in the domain of machine learning. Like you have models where you can predict stuff and you can show like future importance, but causality has been something that's actually been spearheaded by like Amazon and Microsoft recently. So like Amazon has a package called DoWhy, where they're mostly using it internally for like trying to understand like why people buy stuff. So like applying it to marketing or sales. But I know some people like at Oak Ridge who are using it to try and understand materials properties. And for my own stuff, I've been trying to apply it to different data sets, like the Duke MRI, the tabular section of the Duke MRI, or the Wisconsin breast cancer data set. So it's it's not perfect because you still have assumptions that you're making to kind of like precede the causality. So with DoWhy, you have to come with your own hypothesis to start with. So if that hypothesis is correct or incorrect, like you're introducing some bias at the beginning. But that's with the DoWhy architecture. With Lingam, which is what I'll talk about today, it's a linear non-Gaussian acyclic model. So it relies on utilizing linear properties to try and explain causality. So it still suffers from the curse of linearity in that it's not able to capture nonlinear relationships. But this is a pathway for introducing causality or doing causal studies. It assumes that your data is non-Gaussian, which may not be good because a lot of data sets are Gaussian, but it also assumes that you have an acyclic graph. So like 1 goes to 2, goes to 5, but 5 doesn't go back to 1. So it assumes a certain structure of graph, like 1 causes 2, causes 3, 2 causes 5, etc. So it's an interesting linear model, which is a unique approach to causal inference. It's very fast to train. It depends on the data being non-Gaussian, and uh, you need to have the confounders removed. So you have to do some initial cleaning as well. So I have an example here as well where uh, you can use something, you can use this to get started with your own data sets. I'm using the Duke MRI dataset, which I've already kind of pre-cleaned, like labeled anomalies and stuff, but this one runs much faster. So let me get this one going. But this is just utilizing the scikit-learn package mostly. So scikit-learn is the place to start if you want to do anything with tabular data. There's a lot of tutorials. There's a lot of really easy models that you can immediately use, which are very powerful. But in this case, we're going to be utilizing a random forest regression algorithm to predict the days to last local recurrence-free assessment from the date of diagnosis for a set of 922 patients. So we're pulling in the Duke MRI data set. This is the tabular section of the data, and we're going to be doing our best practice thing of creating a train test split. So we create a train test split with 80% going to the training set, 20 going to the test set, and we're utilizing random forest regression with randomized search cross-validation. So we're doing five-fold cross-validation, and we're looking for the best set of hyperparameters for the random forest model. So I'm looking at the number of estimators. So I'm starting with 100 and stopping with 500, with 5 being the interval. I'm looking at the max features, like whether I should use auto or square root to determine the number of features. So square root of n estimators. And I'm looking at the depth. So these are all parameters that I'm tuning. And I'm tuning these automatically to find the best model to try and describe from the descriptors how to predict the number of days to last local reoccurrence from admission. So we're able to train a model and find the best model. So these are the best set of parameters that were used, or this maximize the score or minimize the score in this case because it's using the negative RMSE. But we optimize the model and we find the top features, and then we can use those to create a causal graph. So we trained a model, we can use that model to make predictions, but we can also use that model in the context of Lingam to create a causal graph to try and understand the relationship between the days to less distant recurrence-free assessment. So this is basically what we come out with at the end of the day. We see that adjuvant radiation or adjuvant anti-HER NEU therapy is strongly related to having a reduced number of days to to distant reoccurrence-free assessment. So actually having anti-HER therapy is a good thing. We see that menopause strongly is related to the number of days to surgery. And all of these values are actually in terms of number of days. So whether the patient has began menopause at diagnosis is kind of a big predictor here, along with the molecular subtypes of the cancer. So this is something which we wouldn't have gotten out of a standard machine learning model, is this graph. So this graph is very insightful, and this took like 5 minutes to train with about 1,000 data points. So it's a very powerful technique. This is something that I would encourage people who are working with tabular data to explore. And this is something that is kind of emerging as like a more important aspect of machine learning, is being able to explain causality. Large language models are kind of being thought of as the brain or like the knowledge base. You have a bunch of knowledge, but you need causality on top of that to explain like why things are happening. So like causality is looking to become like the frontal decision-making thing to the knowledge base of the rest of the brain. But this is a simple technique that I would encourage people to look at, and I'm very happy to show people how to use. But
Very intriguing. An interesting approach, just like molecular subtype coming around being predicted of days of surgery.
yeah,
I would assume like more aggressive.
yeah. And it looks like there's a strong relationship to age as well. Like it, in my opinion, it should be the other way. Like the arrow should be pointing towards molecular subtype, but it's still interesting to see that the age is related to the molecular subtype.
Did you limit this in the model? So we have 10 points on this?
In terms of nodes, let's see,
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10.
10?
Yeah.
So I'm gonna guess that there's something that you said that pick 10 out.
So I took the 10 most important features that were learned from the random forest model. So you can determine like which features are most important to predicting the endpoint in random forest based on the number of times they show up in the decision tree. So that process can be automated where you pick the top 10 most important descriptors, and then you can use those to build a graph.
But theoretically, you could choose 15, 20.
Yeah, you can use all the descriptors if you wanted to, or the top 3. Yeah. So yeah, this is a interesting tool, and I'm actually trying to see if we can extend access to this through another project that I've been working on with a friend. we have a causal dashboard that I've been building with a friend. Let's see if it comes up. So the idea is to make it easier to do, to do machine learning. The idea is you can bring your own data. So you can just drag and drop a data set. Let me see if I have one here. Maybe I don't. Let me grab a data set real quick, the Duke data set. But the idea is I'm trying to create a dashboard where anybody can just drag and drop their data and actually start doing machine learning in a simplified way. So let me just pull this data set and I'll show how to use it. So it might be a little slow, but the idea is you can pull in your own data. You can view it, you can do data cleaning, you can determine feature importances, you can generate a graph like we saw using Lingam or utilizing do-why. So this is like still kind of an early stage project that I'm working on, but this will be available at causallab.io like within the next week or so.
What was the data cleaner where you define your endpoint?
Yeah, so you would define your endpoint. So days to last distant reoccurrence, and then you can specify the NA values, and you can do data cleaning, you can drop columns, you can look at feature importance, you can generate the Lingam graph and download it. So this is something that we're building to try and democratize like simple machine learning stuff. Like here you can see the data balance as well. And then you can do like automatic sampling. There's some PCA stuff. Right now it's running slow. But you can do PCA and you can look at the distribution of clusters. You can look at how many principal components you need to describe the data. So this is something that we're going to be making available as kind of like a dashboard for machine learning discovery, like within the next week or two, but it's still something that we're building. Like right now, it's not even associated with the domain name. I just have the IP address set up and it's running on AWS, but this will be something that will be available like in a week or so for people to play with.
I can see this being really fun for like interface type data, where it's like something in like, I mean, a type of neural body, I know, but I mean, it's like a database. It'd be fun just drop in, even if it was like you manually procure data set of like a couple hundred people and define like a second treatment or the collection. I think like it'd be fun to do this for it's just also
Yeah.
It'd be fun just to see the random associations. I mean, assume that if you were going to redo that with like a just a standard multivariate model, how much relationship would be potentially seen into like predicted variables?
Yeah. Yeah, it's a very flexible dashboard. Like we can add in like features as well. Like I want to make it available to researchers here at WashU to like learn how to make it better. But this has been something that me and a friend have been building like in our free time. So we've also talked about like making it accessible for imaging data. So like you can just drag in like DICOM files and generate like vector embeddings and then like try and do something with like MedSAM since that's pretty easy. So yeah, this is like an early stage product that we're kind of like building for people to test out and learn some stuff from. But yeah, let's see. But yeah, I think that's it mostly in terms of slides. I do have the notebooks available to everybody to check out on their own time. So I would be happy to like go through those with people individually, like if they're interested in training a segmentation model using a UNet or utilizing MedSAM, or if they're interested in causal inference. So these are all things that I can help anybody who's interested in utilizing this for research, get started and then run it on the CHPC. But yeah, that's it for my side. Yep.
Any questions? You got me highly intrigued about this puzzle. Maybe that.